Right. Thank you very much to Anand for the invitation, and thank you very much to Angeliki for setting up the seminar. And I wasn't expecting her to be there. Hi, Angeliki. Thanks for coming, and thanks to everyone in Imperial and in Cambridge for showing up. And if it all goes well, I'm not entirely sure how well it is going, but
yes, okay.
I'm going to set this now. I'm also speaking in front of an audience in London. So here's what the talk's going to be. I'm going to say something about what Fermat's last theorem is in the history, and especially because I'm talking to computer scientists, I figured, in Cambridge, I'd say something about the early role of computers in tackling Fermat's last theorem, and then I'm going to say a little bit about the proof, and I'm going to say a little bit about my strategy for this kind of crazy idea I have, where we're going to formalize it. Okay, so here's the history. This is a long time before Fermat. This is 3,500 years ago, and this is the Babylonians. So this is way like before Euclid and everything. This is really a long time ago. The Babylonians writing down solutions of x squared add y squared is z squared in positive integers. So I mean, I don't know if they even knew this whole right angle triangle business, but independent, like Pythagoras' theorem is about real numbers, right? So you can still ask about integer solutions, whether or not you know the relationship to triangles. And you might just imagine that the first one would be 3 squared add 4 squared is 5 squared. But the Babylonians all worked in base 60 because like they had 60 fingers or something. I don't know why, but everything's in base 60, and they really liked numbers which were multiples of 60. And so the first one is 119 squared add 120 squared is 169 squared. That's the first thing, and it's all written in this kind of crazy base 60 notation that they had. So there you go. That's Diophantine equations, even before Diophantus. So Diophantus was about 1800 years ago. He was a Greek mathematician, and he was interested in explicit. So they hadn't invented zero or negative numbers at this point. So he was interested in explicit solutions in positive integers or rationals to polynomial equations, because they hadn't invented sines and cosines either, things like that. So we're a long way from differential equations, but polynomial equations, you know, you can make sense of that. You need to know very little about mathematics to talk about polynomial equations. So here's an example of the kind of equation that Diophantus was interested in. Y squared is x to the 8 add x to the 4 add x squared. So Diophantus raises that question, and he says, now we have to solve it. And he can't, you've got x and y is 0 is no good because they haven't invented 0. So they've got to come up with a solution in positive integers, which is sort of positive rationals, because they had invented positive rationals. So that's kind of tricky to do. That's like a big, that's kind of a complicated degree 8 equation. I guess you can sort of divide both sides by x squared. Right, you never have to worry about dividing by 0 because they haven't invented 0. So you divide both sides by x squared, and then you get a degree 6 equation, but it's still kind of complicated. And this is what Diophantus did to solve this equation. He said, why don't we try y equals x to the 4 plus a half? So he knew about completing the square. He's like, why don't we try y is x to the 4 plus a half? And then when you square y, you get x to the 8 plus x to the 4, which is almost right, but then you don't get x squared, you get a quarter. And so x to the 4 plus a half isn't always going to work, but if x squared happened to equal a quarter, then it would be perfect. And indeed, x squared equals a quarter. We can arrange that because a quarter happens to have a rational square root. And so let x be a half, and then y is a 16th plus a half, which is 9/16. And there we go. And he's found that equation. He solved that equation. And then for Diophantus, that's done, right? Because the game for Diophantus was just to find one solution. And so nowadays, so he wrote 13 volumes of this stuff, 10 of which have survived. Nowadays, any polynomial equation in one or more variables that you have to solve in integers or rationals is known as a Diophantine equation. Obviously, you can solve it in the reals, but that's really, if you allow square roots of things, you know, it's much easier. So solving it in the rationals is hard. And this is a Diophantine equation. So as I mentioned, Diophantine only wanted one solution, but nowadays you can ask for all the solutions. And that's a much harder problem. And in fact, it was realized only, I mean, I guess suspicions were raised after Gödel, but it was realized only around in the 1970s, that actually there's no algorithm which will solve all Diophantine equations. And that's great. So that means a corollary of that is if you're, that's you've got real job security if you're a number theorist, because it just means like no one's going to come along and come up with some algorithm that answers all the questions we're interested in. So yeah, this is an undecidable problem. But for concrete equations like that, of course, that's just because there's no algorithm which will do all equations, that doesn't mean we could, of course, still take one equation and try and do it. And Diophantus just asked for one solution, but you could ask for all solutions to that equation. And in fact, I think there aren't any more, apart from there are sort of negative ones and things like that. But in positive rationals, Diophantus has the only one. And that was only proved in 1996. So that's a really hard, because it's a high degree equation. We're going to be talking a bit about low degree equations later, and you can do those with more basic techniques. But there you go. In 1996, when I was at Berkeley as a postdoc, a PhD student called Joe Wetherall, he managed to solve that equation. So this is kind of difficult stuff. So that's what an equation looked like to Diophantus. I don't know what was going on there. So alpha is 1 and beta is 2. It's like a code. And so that's Diophantus writes that thing there with lots of Greek symbols in. The upside down, the pitchfork, the upside down psi is the minus sign. And just after the minus sign, we've got 2x squared. And that's the delta v means raise the variable to the power 2. And beta is the second Greek letter. So beta is the number 2. So there's 2 occurrences of the number 2 there, but you don't see beta. Diophantus didn't have an x to the n function. He just had something that meant square the variable and something that meant cube the variable. Like the first, that kv is like k for cube. Kv means cube the variable, and then kv alpha bar means cube the variable and multiply it by 1. And then delta v beta bar means square the variable and multiply it by 2. And when he was doing things like x to the 8, he would like do things like square the variable, square it and then square it and then square it and then square it and multiply them together. So he didn't have the power function in some sense. He couldn't raise. All of his equations are completely. I think degree 8 is the highest he ever got, but he never talked about x to the n, and of course that's what Fermat's last theorem is all about. So I don't know if Diophantus could even write down Fermat's last theorem, because somehow he didn't have enough machinery to write down x to the n, but that's what it's all about. So historically attributed to Fermat around 1637, the question is, are there any solutions to x to the n, y to the n is z to the n in positive integers when n is bigger than 2? So we've known by this point for 3,000 years that there's loads of solutions when n is 2. But what about when n is bigger than 2? And obviously, if you let x is 0, then it's easy. But if x and y and z all have to be positive, and if you let them be reals, it's also easy, because 1 to the n add 1 to the n is the n through to 2 to the n. But if you make them be whole numbers and positive, then it's suddenly a very difficult problem. And you can argue that that's not actually a Diophantine equation, because Diophantus wouldn't allow x to the n. So you can either say it's an infinite family of Diophantine equations, or you could say it's one exponential Diophantine equation. You can generalize what you mean by a Diophantine equation. But I would imagine that someone could have explained to Diophantus that question. So Fermat had a copy of Diophantus's volumes, and he raised the question in the margin of his copy, and he also wrote that he found this marvelous proof, but no one ever found. He never published the marvelous proof. The question stayed open for 350 years, and to be quite, the only proofs we know of this. So this thing is now proved, but the only proofs we know are sort of very complicated, and there's no evidence that Fermat actually. He probably wrote this thing like 10 years before he died. So he would have written it and then realised the next day that his marvelous ideas were all wrong, but somehow couldn't find where he'd written it in the book or something. It wasn't like he wrote it and then he died the next day or anything like that. And so he probably didn't have. He probably made a mistake somewhere. One can conjecture where the mistake is. In fact, I'll be doing that in a minute. So this is the conjecture. This is known as Fermat's last theorem. There's no solutions in positive integers to x to the n, y to the n is z to the n, for any n bigger than 2. And the first reduction you can make is that if n is c times d, and if you've got a solution to x to the n, y to the n is z to the n, then you've got a solution to to like x to the d add y to the d is z to the d, because you just use the old x and raise it to the power c. And so somehow, if you've got a counterexample for a large n, then you also might have a counterexample for any divisors of n that are also bigger than 2. And so now the question becomes, what can we say about divisors of numbers that are bigger than 2? And the observation is that if you're a number bigger than 2, then either some odd prime number goes into you, or if no odd prime goes into you, then your factorization just wants to be loads of 2s. So you're like 4, 8, 16, whatever. But in particular, you're a power of 2 bigger than 2. So in particular, you're a multiple of 4. So every natural number bigger than 2 is either a multiple of 4 or a multiple of an odd prime. And so it suffices to deal with those two cases. So n is 4, n is an odd prime, and Fermat did n is 4. So in some sense, this is more evidence that he couldn't do it. Fermat did write down the solution for n is 4, and what he did was he proved that if he had a solution, then he could find a smaller one. That's what he did. In fact, he did x to the 4 add y to the 4 is z squared. He proved that if there was a solution to that, then he could manipulate it and find a smaller one. So that's called a descent argument. So that proves there's no solutions, because you can't keep finding smaller and smaller solutions. So now we've just got to do the case of n is an odd prime, and then the next big breakthrough was made by Euler, where he managed to do the case n is 3 in just the same way. If there's a solution, then after a lot of cunning manipulation, he came up with a smaller solution in positive integers. So those are descent arguments. But as you'll know, if you've got a PhD in arithmetic geometry, descent theory works on curves of genus 1, and as n goes up, the genus goes up. And so for n at least 5, the genus of x to the n and y to the n z to the n is n minus 1 times n minus 2 over 2. So these curves have got very large genus, so you don't expect descent theory to work. And so now people got stuck for quite some time. And even x to the 5 add y to the 5 is z to the 5 is very hard. If you just imagine, if you're good at puzzles, if you're good at Olympiad stuff, and you know an undergraduate degree in mathematics, then you're probably, then you're all on par with Fermat. But you're going to really struggle proving Fermat's last theorem for n equals 5. So what are we going to do? Okay, we're going to go off in a digression. So I have to talk to journalists now because my life's got all weird. And the journalists say, well, what's the point of Fermat's last theorem? And I don't have a good answer to that. And so I just tell them the truth, which is that the whole thing is completely pointless. And it's just, in terms of applications, there are none. But so why are mathematicians so interested in the question? It turns out it's a good question for another reason, because it's inspired mathematicians to generate a whole lot more mathematics, sort of in an attempt to solve in mostly failed attempts to solve the problem. So people have invented sort of conceptual, complicated things, and eventually we invented enough conceptual, complicated things to solve it. So it's driven a lot of mathematics. And I'm going to give a basic example of something that was driven by it. So I'll talk about how I hope to stimulate growth in the ITP community, but before that, let me explain some growth in the mathematical community that came from Fermat's last theorem. And it's all to do with trying to understand factoring. And we're going to start with the observation that if you've got two nth powers, then their product, everything's a positive integer. If you've got two nth powers, then their product is an nth power. That's great. And then you can ask about the converse, and the converse isn't true because, for example, 8 is a cube, and 8 is 2 times 4, and 2 and 4 aren't cubes. And the reason for that is that 2 goes into 8 3 times, and like some of the 2's are going into one factor, and some of the 2's are going into the other factor. And so how do we stop that? And we demand that A and B are co-prime. So if A and B are positive integers and they've got no common factor other than 1, and if their product is an nth power, then it is true that they must both be nth powers. So that's a statement of a theorem, and the theorem doesn't mention prime numbers at all. But to prove this, you have to do a sort of a prime by prime analysis. So the proof crucially uses prime. You've got a prime number, and it goes into this. It goes into 8. It goes into the product n times. and it can't go into both of them because they're co-prime, so it must go into one of them n times. But now you're using the fact that somehow things are factoring uniquely into primes. It's all not obvious unless you think very hard, but you're using the fact that things factor into primes and they factor uniquely into primes. So that's, you know, and that is true, right? Every positive number factors uniquely into primes, and so there you go. And so more generally, if you've got lots and lots of numbers and they're pairwise co-prime and their products in nth power, then they must all be nth powers, and that's an incredibly strong result somehow. And so the idea is, why don't we attempt to use this kind of idea to prove Fermat's last theorem? That's the naive idea. And so we need to find, well, we've got x to the n in, so we've got nth powers, but where's the product of lots and lots of numbers? And the trick is that we don't just work over the integers, we allow a complex number into play. So x to the n, y to the n is z to the n. So we rearrange x to the n is z to the n minus y to the n. So x to the n is an nth power, and now z to the n minus y to the n isn't a product of lots of things, but actually if you allow this complex number e to the 2 pi I over n, then it's like difference of two squares, right? Z squared minus y squared factors. But what I'm saying is if you allow nth roots of unity, then z to the n minus y to the n factors. The reason the difference of two squares factors is because we allow square roots of unity, plus or minus 1. So throw in a complex number, and we can factor the right-hand side, and that's great. So now we've got products of loads of numbers as an nth power, and if you can prove that they're co-prime, which they often are, then we'll be able to deduce that they're all nth powers, and that gives us a highly non-trivial piece of information, and then we can go on and try and prove Fermat's last theorem that way. So that would be great if it was true that once you throw in this one complex number, you retain the property that everything's uniquely a product of primes. So it turns out that that's all you need, right? If you do throw in this complex number and we get a new number system and it still has the property that everything factors uniquely into primes, then you can prove Fermat's last theorem. And in fact, you can prove much more than that. You can prove anything, because this is unfortunately which is a shame. And so that conjecture, Fermat thought that maybe that was how it works. You know, maybe that's so that assumption is false. And the uniqueness of factorization into primes is something that's true for the integers, but doesn't survive more generally. And it was worked out sort of by the German school in the 1900s, how to fix, or the late 1800s maybe, how to fix this kind of thing. There's some concept of an ideal number, so numbers, ideal numbers contain numbers, but they also contain other things that aren't really numbers. They're sort of a slightly more general thing. So a number generates a principal ideal, but there might be some non-principal ideals, and every ideal number is uniquely a product of prime ideal numbers. So slightly generalizing the concept of number, you recover this thing that everything is uniquely a product of primes. But now the problem is we've thrown in some more numbers. We've got these weird ideal numbers that might not be numbers. So you can take the ideals and you can sort of say that you could say two ideals are equivalent if their ratio is a principal ideal, if their ratio is an old-fashioned number. And then you can look at the equivalence classes and you get some kind of finite group that's just sort of come out of nowhere. This random finite group, which is somehow measuring whether factorization works or not. If this group is trivial, the trivial group, then all ideals are principal. So ideal numbers are the same thing as numbers, and things factor uniquely into primes. But if this group is non-trivial, then this is an obstruction to proving Fermat's last theorem. So there we go. So we're trying to prove Fermat's last theorem, and we've come up with this definition of this strange class group, this mysterious finite group. And if that class group's trivial, if the class group, so there's one for each natural number n, and if that class group's trivial, which is for n equals 3, for example, it is the trivial group. And for n equals 5, it's the trivial group. So now you can prove Fermat's last theorem for n equals 5. Once you've proved that this group is trivial, then you can prove Fermat's last theorem for n. So that's great. And in fact, the only thing is, it's more general than that. We can do better, because the only thing we're worried about is taking nth roots. And so if in this funny group, if everything has a unique nth root, so I guess we're only interested in the case when n is prime. So Kummer showed that if this funny group CP has order prime to p, it might not be the trivial group, but if the problems with factorization are somehow problems which are in some weird sense prime to P, then this proof will work. So this was state of the art in 1847. Fermat's last theorem was true if you can prove that P doesn't divide the order of this group CP. So those primes are called regular primes. And now, of course, your next idea is let's try and work out what the first few regular primes are. But computing these finite groups is phenomenally difficult because by the time you've thrown in this complex number, this 200th root of unity, you've generated an extension of the rationals of degree 200. So you're trying to do calculations in 200-dimensional vector spaces. And this gets very slow. So you can work out these groups, but only if you start assuming these incredibly profound conjectures like the generalized Riemann hypothesis. So for any of these 1,000, you can't work these. It's not known. I don't think we know the order of the group Cn for any n bigger than 1,000. So we can't compute these things. But of course, if you're a mathematician, you're not remotely worried about that. You can still develop theory. It's just you might not have any concrete applications. So Fermat's last theorem has led to the study of class groups, and then from these class groups, it was realized that these class groups were Galois groups, and there was this funny link to Galois theory. The next thing you know, we'd invented class field theory, and the main theories of class field theory, these were like the highlights of late 19th century mathematics. And then techniques coming from topology were used to generalize and simplify the proofs. So then we had a fancy modern version of class field theory in the first half of the 20th century. And then in the second half of the 20th century, it was realized that class field theory was just a special case of the Langlands philosophy. It was the GL1 case of the Langlands philosophy. And now we've got a GLN case of the Langlands philosophy, which is widely open even when n equals 2. And in fact, Andrew Wiles proved a small chunk of the Langlands philosophy for GL2. And deduce that was the thing. That was what got us to Fermat's last theorem. We had to move beyond GL1 to GL2. We had to be slightly non-abelian. So all of this mathematics, you can kind of trace it back to people trying to prove Fermat's last theorem, and then basically they found the right question. So that's the history. Now, what about computers? Well, as is often said, the first ever computer program was written by Ada Lovelace, who never actually got to see a computer. And it computed Bernoulli numbers. And what's the point of Bernoulli numbers? So the point of Bernoulli numbers is they're related to this. So there's the definition of a Bernoulli number. E to the t is this exponential function, and you write it as a power series, and you work out this power series on the right, and it's just some big mess with lots of rational numbers in. And then you expand it out as an infinite sum, and the coefficients, which will be rational numbers, are the Bernoulli numbers. So just to give you some feeling as to what they look like, they get quite complicated quite quickly. And that's what these coefficients look like. So there's a definition of, you just manipulate some power series, you expand it out, and you look at the coefficients, and these are Bernoulli numbers. And why are we interested in Bernoulli numbers is because 3 years after Kummer had proved this thing in 1847, in 1850, he proved that a prime was regular if and only if it doesn't divide the numerator of any of these Bernoulli numbers. So now we don't have to work out these class groups, because working out Bernoulli numbers is the kind of thing you can do on pencil and paper. And so now we can work out what the first few regular primes are. So because now we have an effective algorithm that that can be run by computers, which back then were humans. So let's take an example. This Bernoulli number B32 I mentioned, as anyone who knows their 37 times table will know, this numerator is a multiple of, if you know the multiple of 37, you split it up into 37 divides 999. So you split it up into groups of 3, and then you add up the groups of 3, and you get 1,295, and you know that 1,296 is 36 squared. So it's 36 squared minus 1, so it's 35 times 37. So that numerator is a multiple of 37, so 37 is an irregular prime. And actually, it's the smallest irregular prime, which means that after so by 1850, Kummer had realized that he could prove Fermat's last theorem for all n less than 37. So this was the smallest unsolved case of Fermat's last theorem after Kummer's work. And I should say, actually, there's people in the room I'm in that were involved with the lean formalisation of Kummer's theorem. We have Fermat's last theorem for regular primes formalised in lean now. So that's great. So now the question is what to do with 37. And Van Diver found a trick that would deal with 37. And then he found some more tricks. But people kept finding more irregular primes, and then there were more tricks, and sometimes the tricks worked and sometimes they didn't work, and there were tricks, and then but beyond some point, to check that the tricks worked, you had to really do some very lengthy calculations in vector spaces of large dimension, a dimension about n. So by the time they're up to n equals 100, these are very tedious calculations. So in the 30s and 40s, Van Diver had these students that were bashing things out by hand, and they got remarkably far. They proved Fermat's last theorem for all n less than 619. So that was the state of the art. And then the electronic computer was invented, and Derek and Emma Lehmer had access to one in Berkeley, and they checked Van Diver's. Unsurprisingly, Van Diver's students had made mistakes, so they did the whole calculation again in a much shorter period of time. This has taken Van Diver, it was years of Van Diver's life to do this, but somehow in a matter of hours, they had Fermat's last theorem for all p less than 2000. And so there's a remarkable early contribution of computers to Fermat's last theorem. But on the other hand, it was kind of also clear that these tricks weren't going to work, unfortunately. They weren't going to prove Fermat's last theorem in general. For any n, they'd resort, there was a sort of a finite calculation that you could do. See, you can't, Fermat's last theorem is not obviously a finite question. Van Diver had techniques that reduced x to the n plus y to the n z to the n to checking a finite amount of stuff. And if it worked out, then there were no solutions. But it wasn't clear that this was going to lead to a general proof. And in particular, this problem about when p divides the class number, p divides the size of CP, then this prime is called irregular. And unfortunately, it was now known that there were infinitely many irregular primes. And so it wasn't entirely clear that it was somehow worth continuing with this technique. So, somehow. But I think by the time that Wiles announced his proof, I think Fermat's last theorem was known up to something like 4 billion or something. But it was equally clear that this was not going to prove for all n. So in the 1980s, there was this revolution, this observation of Fry. So now we're going to do something completely different. This is the proof that works. So n is a prime number. Let's say we've got a counterexample, a to the p and b to the p is c to the p. Then we can make an elliptic curve. So a, b, and c are concrete numbers. X and y are variables. And this degree 2 equation here, sorry, degree 3 equation in 2 variables is an elliptic curve. And the weird thing about elliptic curves is that you could look at the solutions to that equation in x and y, and you would imagine that that would just be a set of pairs of complex numbers, or a set of pairs of real numbers, depending on whether you're looking at real or complex solutions. But all the complex solutions to this cubic equation, if you throw an extra point at infinity, which is going to be the identity element of our group, it turns out that these things form a group. And the group law is traditionally written as addition, so the identity element is 0. And the crazy thing is three elements of this group add up to 0 if and only if they lie on a line. And the fact that this gives you a group law is a complete miracle. So there's some profound mathematics going on here, but this was known 100 plus years ago. The solutions to cubic equations in 2 variables form a group. So we've got this random group that's kind of fallen out of the sky. And so now what Fry observed is if we take this counterexample to Fermat's last theorem, and then we make this elliptic curve, and then we look at the complex solutions, and that gives us a group, and then you can ask, what are the elements of the group such that when you add them to themselves, p times you get 0? That's the question. What are the points of order p in this group? So these are random pairs of complex numbers, and you look at all those complex numbers, and you throw all of them in, right? Just like we threw one complex number in before, you throw all of them in to your integers, and now you get a gigantic, complicated thing that you can't work out any examples, right? Because to work out an example, you need a counterexample to Fermat's last theorem, and we can't find one. So, but we still know that they will generate some kind of large number system, and we can start analyzing that number system, even though we can't see one single example of it. And one thing we can ask about this number system is which primes are going to behave badly, which primes are going to become squares and cubes, which primes are going to start ramifying in this number system? And the answer is, if you know some general theory of elliptic curves, the answer, if the three roots become equal modulo some prime, then you've got a problem. So if you've got a prime dividing A, B, or C, then this number system will somehow be problematic at those primes. And A, B, and C are going to be gigantic numbers, because we've been looking for solutions to Fermat's last theorem on computers and we can't find any. So you imagine A, B, and C are gigantic numbers. P is a gigantic prime number. We've got this gigantic number system that we've made by throwing in complex numbers. And what we know is that this number system is going to be misbehaving at the primes dividing A, B, and C. Because when you reduce the equation misbehaves, and so the number system will misbehave. So this is the idea. This number system is going to be bad at the primes dividing A, B, and C. And A, B, and C will probably be very large numbers. But then the observation of Frey was that actually you're taking points of order P in some group, but you've got pth powers of equations, and the pth powers of A and B somehow cancel out the points of order P thing, and your initial suspicion that this number system would be very bad at the primes dividing A, B, and C, things magically cancel. This is the weird thing. You would expect this number system to be very big and very poorly behaved to lots of primes, but Frey observed that somehow the P's in the equation and the pth roots of the identity element of this root cancel out, and some miracle occurs, and you end up with this number system, which we can't ever work out any examples of or anything, but actually can only be ramified at P and at 2, because 2 is a weird number. So this thing can only be ramified at 2 and P, whatever it means. 2 and P are the only prime numbers that are behaving really badly in this number system. And maybe they're not even behaving badly either, but all the other primes are behaving fine. So that says that this number system should somehow be small, which is odd, because P is probably a very big number, and we have lots and lots of numbers. So we expected it to be big, but Frey's observation that actually we've got some evidence that it's small. So there we go. So given a counterexample to Fermat's last theorem, we can make this funny number system that's only ramified at 2 primes. So maybe this number system is actually really, maybe all those complex numbers were rational numbers. Right? Maybe they were all whole numbers. Right? Maybe this counterexample to Fermat's last theorem, we threw in all these complex numbers, but maybe they were just all large whole numbers. And so maybe that number system is just the rationals over and over again, right? So is it possible to come up with an elliptic curve where you have a large prime number P and lots of points with rational coefficients of order P in this group? And it turns out, and that was completely unknown for a long time, but in 1970, Barry Mazur showed that actually that can never happen if P is at least 5. This number system must be big. These solutions must be complicated. They can't possibly be rational numbers. So now we've got evidence that this number system is big again, because these random complex numbers definitely aren't rational by a very deep theorem of Mazur. So Mazur's theorem is about 1,000. The paper is like over 100 pages, but it assumes all the work of Grothendieck from the 60s. So I would say probably about 1,000 pages for Mazur's proof. So that's an interesting formalization challenge. And it's no shorter proof, as far as I know, has been discovered since then, since Mazur's theorem. The proof is very, very well understood, and it's been much studied, but it's a very complicated thing. So what have we got so far? We've got to give it a counterexample to Fermat's last theorem. We can make a number system by throwing in some complex numbers on top of the integers, and we know it must be big by Mazur, but we know it's hardly ramified at any prime numbers. So your gut feeling is that this is some kind of contradiction. And in the next breakthrough was in 1990, where Ribbit showed that actually this contradicted the Langlands philosophy. So this is where the Langlands philosophy that somehow comes in. It would contradict this semi-stable Shimura-Taniyama-Wei conjecture. And this was the big. So like no one had a clue how to prove Fermat's last theorem, but suddenly when Ribbit proved that this number field that looked unlikely to exist actually contradicted known theorems, then all of a sudden we've got a root in. This is what made Wiles suddenly drop everything and start working on the semi-stable Shimura-Taniyama-Wei conjecture, because it was such a big prize at the end of it. So Ribbit's paper is another 500 pages of algebraic geometry on top of Mazur's. And then, of course, the next part of the story is that Wiles proves the semi-stable Shimura-Taniyama conjecture. And so, as a consequence, we introduce Fermat's last theorem. And Wiles's proof is another 100 pages, the paper itself. but it's relying on a huge bunch of machinery. And in particular, it relies on all the Langlands philosophy, which is all about harmonic analysis. So all of a sudden, we've got 1,000 pages of analysis. So we've got total like 3,000 pages so far. And so my proposal is we're going to type that all into a computer. So that's going to be interesting, right? But so why bother doing that? Because it's obviously A, ridiculous, and B, pointless. So that's why we climbed Everest, apparently, right? So we should try it because and secondly, I think that it's actually not completely ridiculous. This is the real point. This is not a completely ridiculous idea. It will test the systems, but I suspect that the systems will be fine, right? These interactive theorem provers have existed for decades, and I think that people know what they're doing. So we'll test the systems, and the real reason I want to do it was even if I fail, right? Even if the whole thing turns out to be hopeless, developing this kind of modern mathematics will force Lean's maths library to contain a whole bunch of modern mathematics, and that's where we want to go in the Lean community. We're looking at expanding our maths library so that it contains the kind of mathematics which is happening in mathematics departments. So that's really my current. I've had various visions for what Lean's maths library should look like. So Lean is an ITP, and my current vision. Here's a random thing. Why don't we get it to the point where we can where it actually understands what mathematics is happening in maths departments all over the world. We look at the top, like the important stuff. We look at the top maths journals. These are generalist journals. So there'll be theorems in topology, analysis, algebra, whatever, everything. The idea is, can we get the system to the point where we can actually state those? Because we certainly can't prove them, because 3,000 pages and you've got Fermat's last theorem, but that's like 1992. There's just that every day I get an email consisting of, probably like certainly hundreds and possibly even 1,000 pages every day, 1,000 pages of new mathematics that's been uploaded to archive. We can't ever catch up. But can we at least get to the point where we can state those theorems? Because that's a much more reasonable thing. And we're nowhere near. I think it's a reasonable challenge because I think it is feasible, and we are far from this. And one way of making it happen is trying to prove Fermat's last theorem, because at least then it will get us to that point in number theory, right? An empirical observation is that this is the kind of thing that mathematicians are excited by. When you start telling them that these computers can understand their theorems, even the statements, because a lot of mathematicians still don't realize that that's where the systems are. So in some areas of maths, like additive combinatorics, we can prove modern theorems in real time, right? This is an absolutely extraordinary thing. And so this most recent example was, if you haven't had a talk about this in your seminar, you Cambridge people, you should definitely get one of these people to talk about. Well, I mean, they announced two of these, like Gowers and Tower both got Fields medals, and Green and Manners are also incredibly famous people. So they proved this deep conjecture that was an important conjecture in additive combinatorics. And they put the paper up on archive in mid-November 2023. It's 33 pages. And then Tower announced that he was going to lead a formalization project. And 3 weeks later, it was done. So that's modern mathematics being formalized in real time. That's where we are now. That's really exciting. But in algebraic number theory, we're very far from this. Because in algebraic number theory, it would take us 3 weeks to state the problem. That's the problem. So just to flag people, just random staff members, Rong Zhu and Jack Thorne are staff members in the maths department in Cambridge doing my kind of number theory. And in Imperial, we've got Anna, Toby, and George. And if you take any of these people and you ask them what their most recent theorem is, then absolutely guaranteed there is no ITP out there where you could even state that theorem. It would be a lot of work to even state that theorem. So we're a long way. We're a long way from taking it. I want to take over. We're a long way from taking over. So that's one of my motivations of doing Fermat's last theorem. We'll be forced to build a whole load of modern number theory, which at least will help us to state modern problems. So how are we going to do it? Well, my idea 5 years ago was just, try and get a huge amount of funding together and hire a team and get going. But one thing, it's difficult to get 10 to the $8. I did get 10 to the $7, but that's only going to fund me for 5 years. So we have to think of some tricks. And one of the tricks is we can look at what Wiles did, and we can ask ourselves if if there's a quicker way to the top. And so I talked to Taylor, who was, the co-author of Wiles in one of the papers, and we've discussed some way of doing it. And the idea is we do more algebra, we do more commutative algebra, because commutative algebra is really nice and fun to formalize. And instead of using Wiles's proof of semi-stable Shima-Rotani-Armavay that analyzed the 3 torsion, we're going to do something else. We're going to use potential modularity tricks that Taylor introduced. And we're going to work with the P torsion instead of the 3 torsion and the 5 torsion. And a massive win going this. So now that means we have to do more algebra, but we have to do much less analysis. And we can also skip Ribot's theorem. So this is a big win as far as I'm concerned, because we're avoiding some analysis, right? We've still got to do this theorem of Mazur about these solutions of these points on the elliptic curve never being rational. And we still need all of the algebra machinery that Wiles has developed. And unfortunately, we still need a bit of the Langlands philosophy, rather annoyingly, which is analysis. But it's much more algebraic than it was. And as far as I'm concerned, that's a big win. And it also means the results that we need are historically earlier. Mazur's theorem is 1970. The Langlands results we need are from 1980. And so if we can get to 1980 number theory, I'm going to come down, and other people are going to build up. And if we can get to 1980 number theory, then we've won. And getting down to 1980 number theory is mostly going to be algebra and number theory, which in my experience, in lean at least, is much easier to formalize, right? So why am I trying to remove the analysis? So firstly, that's the part of the proof I understand the least. And that's because actually I've never liked it. It's my worst thing. I was like, the moment I was in 3rd year, I was just doing algebra when I was an undergraduate. I don't like analysis, and so I don't like formalizing it. And I haven't. And the algebra part of the proof I've read. I was a student of Taylor when it all happened. I've read the algebra part of the proof, but not the analysis. And also, another cold hard fact is that Lean's analysis is not as well developed as Lean's algebra. Lean's algebra, we're well beyond MSc stuff. We've done some research level stuff, whereas analysis, we're still kind of behind. And why it's so interesting, like, why is that happening? Why is Lean not very good at analysis? Isabel Hall is ahead of Lean when it comes to analysis, right? That's absolutely clear. For algebra, Lean is just all over everybody. Like, Lean is just, rollicking ahead really, really fast, with people developing, hard modern algebra. Whereas analysis, we're slow and we're behind. We're still not even state of the art when it comes to analysis. So one reason might be that there's this guy called Manuel Ebel, who's very good at analysis and is a very prolific Isabel formalizer. So do we just need some lean version of Manuel? Or is it actually, here's another, so Isabel Hall is an interactive theorem proof that uses simple type theory, and Lean uses a more complex dependent type theory. And so is it the case that actually analysis is easier to do if you have a simpler type theory? Because the kind of analysis that we need, a lot of it is sort of based in sort of 19th. There's a lot of 19th century analysis that we don't have in Lean that exists in Isabel. Before the sort of abstract category theory revolution, it was perfectly fine to model a lot of mathematics in simple type theory. So Terry Tao has now launched a project to prove the prime number theorem in Lean. And so we're going to find out how difficult analysis is soon enough. But there's my thoughts on analysis. Maybe in 5 years' time, Lean will be all over Isabel for analysis, and maybe it won't be. I just don't know. But I did consider other systems, and I think trying to formalize the proof in Isabel would be painful. Maybe the analysis would be less painful. But what I'm worried about is the category theory, because there you do really seem to need a stronger type theory. I think that formalizing category theory in an actually usable way might be quite complicated in simple type theory. Of course, the other thing that Isabel has going for it is it's got better proof automation. It's got Sledgehammer, for example. And again, that might be because it's got a simpler type theory. And so I think within the next 5 years, we're going to find out whether Isabel's automation is better than Lean's simply because Isabel is a better system or uses a simpler type theory, or is it just because no one's written the right automation yet for Lean? So as I say, I think, one thing that will drive, if I'm proving Fermat's last theorem, people might be motivated to try and answer this kind of question. So last thing, then I'll talk about how I'm going to run the project, because as I've tried to explain, we've got thousands and thousands of pages of mathematics, and we're not yet at the point where you can just feed the textbooks into a machine and the machine spits out lean code that works. And so I'm going to have to sort of manipulate people. I mean, maybe in 5 years' time, the AI will be at that point, and we could just start feeding it in. I don't know. I don't know how good AI will be in 5 years, but right now, I need people. So I'm going to run everything as a free open source project, and I'm going to be encourage contributions. I'm encouraging PhD students in number theory, for example. They would be the perfect thing. And the glue that's going to hold everything together is Patrick Masso's blueprint software. So let me show you. This is Tao's. This is let's see if this works. Oh, I might have to. It's just occurred to me that. Oh, okay. So I'm not going to show it you because you can't see it in Cambridge. Oh, maybe I am. Okay, let me briefly stop sharing this. Oh, spoilers. Let me stop sharing. I need to just share a different thing. Stop sharing, and now let me share a window. Let me just share screen. So the thing I was just showing you, which browser was I using? Was it that? Yeah. This is a partially done. So I'm assuming that the Cambridge people can see this.
Yeah, we can.
Yeah.
Great, thank you. This is a partial proof. So green means done, and all the prerequisites are done. Light green means done, but prerequisites still not done, and white means not done. And so you click on something, and there's the lean statement. And now this is a kind of a simple statement, and then you can jump to some LaTeX document. This is something that Tao and Kontorovich have written. This is mathematics, but spelt out, really broken down into lots of pieces. So it's not what you would see in a textbook. It's very, very carefully broken down into much smaller pieces. So that's the idea. So first you process the mathematics by still writing mathematics in the normal way, but putting far more details in. And then when you've broken it down into pieces, then you turn all these pieces into nodes in this graph. And then the idea is a passing mathematician. The point is you don't have to know the proof of Fermat's last theorem. This is the key thing. You don't have to know the proof of Fermat's last theorem to help me prove Fermat's last theorem. You just have to find a blue box that when you click on the blue box, you understand the statement in the blue box. Right? If you don't know all the technical machinery, whatever, it doesn't matter. As long as you can understand what's going on in the blue box, then you can write, this project will take like a day or so. This is a basic formalization project. And so you break it down into tens of thousands of basic formalization projects. And then you try and persuade many, many people to help. That's the idea. So here's my blueprint. So for the Cambridge people, you should now see a much smaller blueprint with some orange in. So my blueprint, the coloring system has got this new orange thing. So green means done, and blue means a nice project that you could do. But now I've got this problem. I've got this thing. Is this number field big or small? Well, Mazur says it must be big, and Wiles says it must be small. So that contradicts the Frey curve thing. And so orange means a gigantic research project. Orange is could be 1,000 pages. And so then we're going to pull bits off. But this is what we have. And so already there's a bifurcation, right? Already I've reduced proving Fermat's last theorem into proving two completely disjoint 1,000. One is 1,000 pages and one is 2,000 pages. But they can be worked on totally independently. So in particular, the Mazur's theorem, that was proved in 1970, and I'm just going to park that for the time. I'm not going to work on that. I'm going to do the Wiles stuff because the Wiles stuff is somehow the sexiest stuff. So I'm going to be working on the Wiles stuff. And Mazur thing, it will just be left as an open issue on the GitHub repository, saying if anyone wants to take on Mazur's theorem, that's absolutely fine. But if no one wants to take it on, I'll finish Wiles and then I'll go on to Mazur afterwards. So we're going live in April. I'm sorry we're not live now. I'm just busy teaching. So this is pretty much nearly it. But this is somehow the important. This is the important thing. As Tao gave a talk at the joint maths meetings of the AMS last week, and he absolutely stressed that this blueprint software, this funny graph thing, enables this really powerful form of, you can get hundreds of people working on one project, and you don't have to trust. If you're trying to prove a theorem in the old-fashioned way, then and somebody comes along and says, oh yeah, I proved this lemma, like they write down the proof in your LaTeX document, and then you've got to check it. But the thing is, the computer checks these things, so you don't have to trust you might not even know this human. There's some random person that showed up on the internet. And the other advantage is that you don't have to know the full proof. You can contribute by just proving a lemma. In fact, like I should say, one of those lemmas, that one there, P03, that's Euler's theorem, right? That was known hundreds of years ago. That thing in the top right, P03, that's proving that there are no solutions to x cubed and y cubed is z cubed. So, I knew how to do that when I was an undergraduate, and I certainly didn't know how to prove Fermat's last theorem. So that's the idea. You find a blue node, and if it turns out you understand the maths, because you can read the LaTeX proof, and if you understand enough about lean, you can fill in that proof, and the blue node turns green. And my idea is hopefully we're going to be getting undergraduate students and PhD students to sort of help us along. So I've got no idea whether this is reasonable. So last but one slide, Lean's maths library already knows the two key players, elliptic curves and modular forms, but there's a whole bunch of things that we need that it doesn't know. So this is my proof that you can't formalize the statements of modern number theory, because here's just a whole bunch of random buzzwords, all of which are missing, and before we prove theorems about Galois representations, we're going to have to state what a Galois representation is. And before we prove theorems about Gorenstein rings, we need to define Gorenstein rings. So there's a huge number of definitions missing, and the project will force these definitions to become formalized. And then last slide, I don't know if we'll do it within the grant runs for 5 years, and I've no idea whether we'll do it within 5 years. It all depends on whether it becomes a thing or not. But I am confident that within 5 years, we can do Wiles's paper. So that will reduce the problem at least to what was known to humans in the 1980s. I think even if no one else joins in and I just work on it by myself for 5 years, I can do the key ideas in Wiles's paper and get Fermat's last theorem down to the 1980s. And along the way, I'll be able to state very precisely the things I will need that other people will then be able to work on independently. So that's the very least of what I hope to get done within 5 years. A reduction of the theorem to facts known, very complicated facts that were known in the 1980s, but which have all been formally stated. And then, of course, the people working on Lean's maths library are going to be working up from the axioms, and I'll build down from the top. And then at some point, possibly within 5 years, but very possibly not, our paths will meet. And we'll be done. And that's it. Thank you very much.
Thank you. We can take questions from the audience.
Okay. Yeah, I'll have questions from Cambridge. Yeah. If there are no Cambridge questions, I can ask Imperial people if they have questions as well.
Oh yeah, I think there are a few Cambridge questions. Yeah.
Okay, yeah, but you should go first because you invited me.
So I was wondering, with recent formalization attempts, we perhaps some of the things which make the theorems work are perhaps better understood, at least according to Schulze. So I was wondering if there's any parts of the proof of Fermat's last theorem which you think would be better illuminated by formalization.
I don't know. Oh, sorry, Alan, were you going to say something?
Oh no, I was just going to repeat the question if it wasn't audible.
No, I heard the question fine. Will we learn more about Fermat's last theorem? We might. There is a chance that we will come up with some abstractions which might clarify things in some kind of superficial way. But I'm not convinced that I'm going to be telling Andrew Wiles that he should have done it like this. I'm not sure. I'm not sure, but I'm not confident. Let's put it that way. That at the end of it, well, we will have a very well documented proof of the theorem, but I'm not convinced that we will have too many new insights. Is my guess, unfortunately. I mean,
There are
we're having the insights already because me and Taylor are writing the LaTeX document. So that's where the insights are happening. But that's, you know, I'm not convinced that the formalization will play a role.
There were a couple of questions.
So my question is, have the lean people made any comment on the undecidable propositions? How do they come up in the MATLAB?
So the question about undecidable propositions in MATLAB.
MATLAB is just normal maths, not crazy logic, so everything is decidable. What do you mean? Like, this whole Gödel proves that there are wacky statements which are undecidable, but me as a number theorist, those kinds of questions don't ever show up in my work. So I don't think we'll be running into any decidability issues. To find weird undecidable questions, you have to try very hard. Yeah, everything is decidable. Everything is true and provable. There's not going to be wacky. We're a long way from logic. We're dealing with numbers. So I think Gödel is not going to be an issue. I don't know if that answers the question. Maybe I misunderstood it. But yeah,
and there was another question.
Yeah, how as a PhD student, well, you can see, how as a 2B PhD student who knows a lot of analysis but not so much algebra how can I help?
Is that Yale?
Yes, that's me.
Hiya. How can you help?
Yeah.
Well, you need to learn some number theory.
Well, if you take it for PhD.
Aha, okay. Yeah, but yeah, okay. Maybe we could do that. Yeah. I guess we shall see. I mean, there might be some analysis involved. Are you any good at analysis? I haven't really. I haven't really thought about. Have you looked at the prime number thing? Have you looked at the Kontorovich-Tau thing?
Yeah. It looks pretty understandable. Only contour intervals are scaring me a bit, but that's fine.
But we need that. We need Chepetarev's density theorem because it's a crucial part of the auxiliary prime argument in the Taylor-Wiles paper. So yeah, you could help by helping me prove by helping Terry Tau prove Chepetarev's density theorem. There'll be lots of stuff. It won't just be number theory.
You've been helped.
Yeah. Are there any other questions? Oh yeah, I'm going to take
Thank you so much for the talk. So regarding testing the system, of course, I know until you do it, you can't really tell, right? But I'm wondering if you have any suspicions about which parts might be more challenging. Of course, you did mention analysis, right?
Yeah, analysis.
Anything else that you think might?
I can envisage that in 10 years' time, everything is done apart from the analysis. That is not a completely outrageous idea, because analysis just seems to me to be going very slowly in Loon. But I don't see any problems with it. It's just I just need time. I don't see any problems with the algebra and number theory. But the geometry and the analysis might be slower. We'll have to do some differential geometry as well, and that scares me as well a bit. So that's my guess. I don't think there'll be any problems, but that might be the hardest work. Trying to get it into a state, trying to turn what's in the literature into formal stuff. My guess is that that's harder to do in those areas. So, but who knows? Yeah, so maybe Yale can help with that.
All right. It looks like we're done with questions on the Cambridge side.
Okay, great. Then do you want to say goodbye? Because it's
we can stick around for the questions on the Imperial side.
Okay, I'll take some Imperial questions and I'll go on. Jeff, you've been waiting ages.
I think you said no. Was it known? Was an algorithm known that would resolve n?
No, but an algorithm was known that were conjecture. An algorithm was known that had never failed. We got to that point.
Conjecturally, it would fail.
There was. I don't think people had a clue. I mean, nobody was trying to prove it always worked. So probably people thought that it would not always work. But given an n, there was a method, and you applied the method, and it worked. Now there's an algorithm, yeah. But yeah, at the pre-Wiles, there was no algorithm. There was just something that had very large chance of working. And that's historically exactly what had happened. Yeah, we had algorithms that just got better and better. By 1992, they'd got up to 4 billion. But you had to compute all those Bernoulli numbers. You had to run Ada Lovelace's program. So that was the big bottleneck, computing Bernoulli numbers. Hello. So the question is, as a first year, which modules should I take in order to help you with the project? So all the pure modules. This covers pure. This is all pure, right? All pure, apart from the logic course, all pure maths. It's absolutely true. I'm not trying to be rude. It's absolutely true. We teach a third-year logic module, which is of no relevance at all to this, and all the other modules are relevant. So there you go, including the lean module.
Lean at Imperial, or will you?
Oh, there's no more questions. Oh, go on.
Oh, there was one question here.
Oh, geez, 10 past. Go on.
Sorry, just first question, because they didn't ask about modules. So I was wondering if you are still teaching lean at Imperial.
Am I teaching lean? Yeah, I'm teaching it, right. That's the reason that we're not getting any Fermat's last theorem done, because I've got 24. Because I've got 24 projects to mark, but in fact they've all been marked. Yeah, I'm still teaching a lean course at Imperial, and it's incredibly hard work. And that's why I'm telling people that we're going live in April, because the course finishes in March.
But you will not continue teaching it from next year?
Oh no, we're hiring, we're expanding in lean. So somebody else will be. The course will run, but it won't be me. Yeah. Imperial Maths is expanding in lean, so we must be doing something right.
Are there any questions from the online audience?
Great.
It doesn't seem like it.
Okay.
Thank you once again.
Yeah, no worries. Thanks for the invitation.
Thank you.
Cheers.